to go back and return to our two example problems, the swimmer problem and the 3 students pulling, which I illustrated with a little block and some strings, to talk about how we actually add vectors using a triangle or a parallelogram. We're going to learn other methods later on in the vector unit. So here was the vector that represented the swimmer's initial velocity. I'm adding some extra information to this. I'm going to say that the swimmer's initial velocity was 3 miles per hour at an angle of 60 degrees to the bank. Remember, a vector has to have magnitude, length, and direction. So its length is 3 miles per hour. Its direction is 60 degrees angle from the bank of the river. Okay, so this represents the river here, and this is the edge of the river, the bank, where she dives in and starts to swim. So then the 5.5 miles per hour is the velocity of the current of the river, and we say this current is parallel to the bank of the river. Now remember, we have to have vectors positioned tip to tail to add them, so I am going to position the velocity vector for the swimmer here, and I'll position the velocity vector for the current here. Now they are in a position to add. And to add them, we start at the beginning or the tail of the first vector and draw a straight line to the tip of the second vector, and that is called the resultant vector. And so when we talk about the resultant angle and velocity, we're talking about the two characteristics of the resultant vector: its length, the velocity, and its angle. So what I specifically want to find out is I want to find out how long this dotted line is right here. That's going to be the velocity. That's the length of the resultant vector. And I want to find out the resultant angle. Okay, so the angle here, the resultant angle, so I'm talking specifically about the angle from the bank. Okay, so she was at a 60-degree angle from the bank, like 60 degrees kind of going to the right. Now she's at a much bigger angle, actually going to the left instead of to the right. Okay, so I do need to add the arrow on here. Okay, so that's the direction she's going. Now, because the current is parallel to the bank, and I know this angle right here, then I also know this angle that's inside the triangle, so I know that this is also 60. So this gives me a side angle side triangle, and now I can use law of cosines to find the length, and I'm going to call this R for resultant. I want to find the length of the resultant. So I'm going to say R squared is equal to 5.5 squared plus 3 squared minus 2 times 5.5 times 3 times cosine of 60. We've done this kind of problem many times before. I'm going to find R by putting all that in my calculator and taking the square root of it. Notice when I do that, I get 4.77 approximately miles per hour. So that is her resultant velocity, 4.77 miles per hour. Now, that is, and I'll go back and show that. I probably should have copied and pasted. Okay, I put in my work here to make it easier for you to see what I just did. Okay, not that it was necessary probably for you to see that. That's the resultant, the velocity. Now the angle, then I know this angle 60. I need to know the angle inside the triangle. So let me just call this angle right here theta. I want to find theta. So once again, I know all 3 sides of this triangle now, and this angle theta is opposite the longest side, so it's not safe to use law of sines to find this angle. I could use law of sines to find the smaller angle and then subtract from 180 to find the larger angle, or I could find this angle using law of cosines. So I'm going to go ahead and use law of cosines. You could also do it the other way. So I'm going to go ahead and set up law of cosines to find angle theta. So 5.5 squared is equal to the angle I just found, or the side I just found, 4.77 squared. And of course I'm going to actually put this in as 4.769 because I'm going to go ahead and copy that in my calculator, plus 3 squared minus 2 times 4.769, etc., times 3 times cosine of theta. So I'm going to take all of this and kind of scoot it over a little bit because it's taking up so much room into my other problem. So I'm going to end up subtracting these two values, 5.5 squared minus 4.696 squared minus 3 squared, then dividing by all of this. So I'm going to go ahead and pause for a minute, do that on my calculator. You can do the same. Okay, I've done all this in my calculator. From the equation on the other side, I've subtracted the two squared terms. From 5.5 squared, I get negative 1.5. I've multiplied negative 2 times the 4.769 times the 3. I get negative 28.618. And so I'm going to end up doing inverse cosine of those two values divided by each other. So I'm going to go ahead and grab a copy of this and move it over so this work will show on my notes page. So you can see hopefully how this works out. Alright, so notice here I subtracted these two values from this one. That's the negative 1.5. So I ended up with negative 1.5 squared equals, then I multiplied all of this together and I got negative 28.618 cosine theta. Then I divided both sides by negative 28.618 and then took inverse cosine to find theta. So I have successfully now found the angle 86.99, which is the angle inside the triangle. So I need to take that angle and add 60 to it to get the full angle that represents the direction that the swimmer was going from the bank. So if I add 60 to this, then I have 146.99 degrees. So my new vector, the sum of my two other vectors, has a length and a direction. Okay, so that's how we determine a vector. It has a length and a direction. Now I want to do this other problem here. And this is, we have two students. One student is pulling with a force of 450 newtons, that direction. The other student is pulling with a force of 580 newtons, that direction. Remember, I have two little students, so this little student was pulling here, and this little student was pulling, and my third little student right here, who was hanging onto the hands of the other two students, ends up going kind of up the middle in the direction. Now, we want to know exactly how much force was exerted on the third student in this direction. Okay, so the force is measured in newtons. A newton is defined as the force needed to accelerate 1 kilogram of mass 1 meter per second squared. So this is a lot of newtons because this student's a lot more than 1 kilogram. Okay, so they're having to pull a little harder. There's a 75-degree angle between the directions that they are pulling, and we want to know what's the resultant force. Now, I just got through saying that we cannot add vectors tip to tail, and we can move a vector anywhere parallel to itself, and it will still be the same vector. So, for example, this vector could move over to here, and now these two vectors are tip to tail and ready to add. Or I could move this blue vector over here, and so these two vectors are now tip to tail and ready to add. Either way, the resultant vector is going to go from the beginning of one vector to the end of the other, from where the two tails are. The tail of the vector is here to the tip. Now, I know because the vectors are just moved that these two lengths are still 580 and 450. But what I don't know are any angles in the triangle yet. And this is the resultant vector. This is the length I'm trying to find, that force, okay? Because these are in forces in newtons, then this will also be in newtons. Now, this is not half of 75 and half of 75. If these two vectors were exactly the same length, then this resultant vector would bisect the angle and divide it exactly in half. But they are different lengths, so this is not going to be half of 75 and half of 75. However, we do know something about that angle. Think about the fact that this is a parallelogram. So if we have a parallelogram, kind of looks like this. And, well, that's not a really good, that made it all look like everything's right angles. Let me do this a little better. So if we have this parallelogram, and these are parallel to each other, and these are parallel to each other. Oh, this is horrible. And I know this angle. Wow, one more try, sorry. I'm just not doing a very good job of drawing this. Okay, I had to kind of make it a little more squattier, but I know this angle. And these are parallel to each other, so I also know this angle. And I also know this angle. So all these angles are the same. So if I know what this angle is, 75, then and that's also 75 and that's also 75. So I know what this angle is, because this angle has to be 180 minus 75. So this angle has to be 105. So that means right here this angle is 105 because this angle is 75. And that's always going to be true when I add two vectors, because they're always going to make a parallelogram, and the two adjacent angles in a parallelogram always add up to 180. So now I have a side angle side, and I can find the length of this side. We're going to do the same thing with the law of cosines, and I'm going to do this a little more quickly because we've just done this computation a number of times. So r squared is equal to 450 squared plus 580 squared minus 2 times 450 times 580 times cosine of 105. Put the whole thing in your calculator, and you end up with r equals 820.98 newtons. So this is how you add two vectors using either a triangle or a triangle from a parallelogram. You're always going to end up with a triangle one way or the other, but sometimes you also have a parallelogram. So if you start out with just some vectors that you can position tip to tail and then add the resultant, you'll get a triangle. If you start out with two vectors tail to tail, draw the resultant in the middle of them using a parallelogram, then you'll use this method here.